Good evening, ladies and gentlemen. Welcome to Lecture 10 of Topic 2 of Unit 4, the photoelectric effect. We're going to be looking at the practical components this time. The video will be continuing with the main ideas of Chapter 11.5 of Book 2. Please complete the reading before class. Here are your learning intention and success criteria. Please pause the video and attempt to complete the KS table down the bottom right. Okay, so we can see here we want you to be able to recognize photoelectric effect experimental data and use it to determine physical properties of the experiment. Some things we should be able to do: determine Planck's constant, a threshold frequency, and the work function from EF graphs. Determine stopping voltage from CV graphs, and recognize when there's some transformation of axes happening here. So in terms of knowledge, well, we need to know what an EF graph is, we need to know what a CV graph is, and in terms of skills, can you calculate those properties? Now, you'll notice I haven't mentioned anything about what's Planck's constant, what's the threshold frequency, what's the work function, what's the photoelectric effect. That was all the previous video. Okay, this video assumes that you've kind of got your head wrapped around this. This is just going to be looking at the graphs and the practical type stuff that you could be expected to understand for your exam. So, in mention in the last video, we've got the following equations for the photoelectric effect. But I'm going to focus on these two. They're the main ones that relate to the experimental data that you could examine on an exam. Now, do keep in mind that this formula, the EK equals QV, is actually in electrical circuits, and it's written like this. It's not under quantum theory. Okay. One of the things that you've got to keep in mind is that we have three topics that essentially look at electrical stuff through this year. We've got electrical circuits, electromagnetism, and then finally parts of quantum mechanics here, or quantum theory at the end of it. And if they have to do with circuits, then it's still all true. It's still a circuit. So let's get into it. Now, as we spoke in the last video, there were two main experiments done. The first was how the energy of the particle, the kinetic energy of the particle, changed in relation to the frequency. Okay. Now, an EF graph, E for energy, F for frequency, is very common when you're doing photoelectric effect experiments because they show a number of critical features and they require you to interpret both the gradient and intercepts. I did say intercepts. So here's a standard graph. Okay, now the first feature you have to understand is the gradient. The gradient on an EF graph, and we can see here we've got an energy and a frequency, okay, will be Planck's constant. If you've got a graph with multiple metals, you can see that the lines are parallel, because all their gradients will be Planck's constant, and if they've got the same gradient, they must be parallel. If you're asked to calculate this from a graph, make sure to use rise over run. Okay, change in y over change in x. Select 4 points, 2 y values, 2 x values. One trick I would use is that I would make my x1 my x-intercept, so that I can say y1 must be 0. That way I've only got to read one more point off the line and where that crosses there. And since that's, if I'm asked to calculate this, I'm probably going to be asked to read that in a second anyway, so it's a good habit. Right. Now, speaking of the x-intercept lets you determine the threshold frequency. And remember the minimum frequency to get this thing going. And it will just be a direct read of the graph. Now, the y-intercept will be a bit trickier. If you can see the y-intercept, then the value will just be the function. The value will be the work function. So, this graph here, we can't see the y-intercept, but we could slap a ruler there and just measure down to it and go, oh, that's where it crosses. That's the y-intercept, which actually wouldn't be an issue. But what if you can't see this axis, and drawing it out would just introduce more error, or perhaps you don't have room for it. So how do we work it out? Now, if you can't see it, you can work it out by multiplying the x-intercept by the gradient. Okay, so the y-intercept's a work function, And we can work it out, the work function, by multiplying the x-intercept, the f naught here, by the gradient. Now, we saw that equation last video, but there is a way to use the photoelectric equation to figure it out if you don't recall. Okay, so using this one, which will be provided to you. This one won't, okay, but that one will. So first off, you have to remember, well, for the x-intercept, the kinetic energy equals 0, because that's what an x-intercept is. The y value equals 0. Okay? And we've got our frequency must be f naught, because that's what we just said over here, that the x-intercept is f naught. So if we take those and make the substitution, we get this, and rearranging, we arrive at the same equation over here. Okay, so if you use the idea of take the x-intercept, multiply by the gradient, you're going to get the y-intercept, then you will be, if you can remember it, great. If you can't, there's a way to work it out. So that's everything you have to be able to do with an EF graph. You've got to be able to do the gradient, you've got to recognize what the two intercepts are. Our second experiment looks a bit differently. These graphs are less common and they're less versatile than an EF graph, but you may need to still interpret one. Now over here on the right, where it says reference beam, is a saturation current. And we saw this happen when we increased the voltage and made the anode more positive. Remember, the names for anodes and cathodes are backwards in this experiment. The current didn't change. But when we reversed the direction of the battery and started applying some negative voltage over on here, we slowed down the current until eventually it reached a stopping point down here. The negative voltage does stop the current. And we can see down here that for some voltage value, the current will be 0. Again, we just need to do a direct read, and that will get us the x-intercept. That'll get us the stopping voltage or the stopping potential. Now, this sort of graph, this one I've provided here, is a little bit more complicated because it has some different references to frequencies and intensities over here. One thing of note, notice that this blue line, the reference beam, though the colours are a little bit hard to see, and this green line here at the bottom, lower intensity, same frequency, they both have the same stopping voltage. Because remember, the stopping voltage here is about how much energy needs to be applied or how much work has to be done to slow down the particle. Okay? And the frequency is what determines how much energy the particle has, not the intensity. We wouldn't see this same stopping voltage with different intensities if light wasn't a quantum particle. It had a quanta and had a discrete amount of energy. Meanwhile, if we have a lower frequency but the same brightness, the same intensity, we see the stopping voltage is less. So if it was intensity that was doing it, then we would see the stopping voltage be the same for intensity, but we don't. So this one is a little bit more advanced, but it is worthwhile understanding. Now, there are some variations that can happen. They're unlikely, but they are reasonably possible. So, we've seen our EF graphs. We've done one in class. We saw it just a second ago with the energy in joules and then frequency across the x-axis. Theoretically, not likely, and the only reason I'm including it is because there is just a reference to it in the syllabus, but theoretically you could get an x-axis with the wavelength instead. And it looks something like this. Across the bottom we have wavelengths, it's measured in nanometers, and down the side there is, in this case it's electron volts, but just read it as energy, it's still reading the kinetic energy, the maximum kinetic energy. You could still work out Planck's constant from the gradient, not the gradient of this one, but the gradient, the threshold frequency and the work function, but you'd need to convert the wavelength numbers to frequencies using the wave equation. Note how here, even though it's curving, that's not where it stops. It would keep going below it theoretically. So you would need to use this formula, the wave equation. It is provided. Remember, v would just be the speed of light. Lambda, in this case the wavelength, we would read off the graph and we'd work out f, and then we'd be able to get a straight line EF graph. I sort of rank the possibility of this happening on an exam, a QCAA exam, as something like 0.5 out of 10. I really don't consider it possible. But realistically, if it did happen, all you need to consider is that you've got nanometers. You need to turn it into frequency because that's what Planck's equation deals with, and that's what the photoelectric equation that we've been provided with deals with. So we do a conversion and then we're good to go. Now, another possible variation would be the y-axis being in electron volts. This is more common. You would have to convert joules, convert these electron volts to joules if you wanted to work out Planck's constant. Okay, or so you can see where it crosses the y-intercept here, if you wanted your work function to be written in joules, not electron volts. So you'd have to use a conversion. Remember, this constant, the 1.6 times 10 to the negative 19, is provided in your formula booklet, and it's the charge, elementary charge on an electron or a proton. The x-intercept would be still a straight read because we've still got frequency. So I could say here, whatever this metal is, the work function is 10 times 10 to the 14 hertz. Sorry, not work function, the threshold frequency. But the gradient you need to convert. Now, there's another very rare one. Oh, sorry, let's rate this one. This one, I would say, has a potential of maybe 6 or 7 out of 10. Like, this is not a hard one for students to work with. The trick is that your y-axis is not in joules, it's in electron volts. But all you'd have to do is convert one number, because remember, if you were smart and used your x-intercept as your y1, x1 component, well, y1 would just be 0, and your x1 would be a direct read, x2 would be a direct read. You just have to convert that from electron volts into joules. This last one is possible because this is the original experiment. Instead of using kinetic energy on the y-axis, instead it plots stopping voltage. And you notice here that it's a straight line. So it's very much related. So this must be just another transformation of energy here. The y-axis, so the x-axis is just the standard. It's frequency, it's in hertz, it's 10 to the 13 over there. We could read the intercept and go, yep, that's a threshold frequency. But the stopping potential is in a different unit. It's in volts. It's not electron volts. It's in volts because it's talking about, well, what voltage did we have to apply to stop this from happening when each of these different frequencies. This is what Leonard's actual experiment was. Remember though, we can turn that stopping potential into an energy, okay, because we've got this equation. Okay? The kinetic energy of the particle must equal the work done to the particle to stop it moving. Remember, work is just energy. Work is think of it like a change in energy. So if it had kinetic energy and we made it stop, we did some work. And the formula, work equals QV, is provided, though I believe it's V equals work over Q, but the formula is provided to you. So you could potentially have this, and you would just have to, again, convert a Y value into joules so that you could work out Planck's constant, or convert a Y value into joules in order to work out the work function of the metal. If you could read the straight line, though you could always take this F and just multiply it by H, as we've seen before. So this one has a bit more potential. I would say maybe, actually, I probably wouldn't even say 6 out of 10, maybe 4 out of 10. It's got a potential, but this would be thrown in as a sort of, let's really make it a tricky type of question. Now, the last variation is just the magnitude of units. This is a good graph to pay attention to. Now, keep an eye out for scale on the axes, as often you'll get numbers provided that have the powers listed in the units. So if you forget to include them in the unit in your calculations, you'll have a problem. So if you were to read this and go, oh yeah, the work function, so the threshold frequency for this is about 4.5, you'd be wrong, because it's not 4.5, it's 4.5 times 10 to the 14. Okay? And if you were to go, well, it's about 7.8 take away 0 divided by 16 take away 4.2 or 4.3, whatever it was I said before, and that's Planck's constant. Again, no, we'd be wrong, because we haven't included the times 10 to the negative 19 joules up there, and we haven't included the times 10 to the 14 hertz down there. You get the right magnitude, you get about 6.626, but your power would be way off. So, this one, that's something that you are going to have to keep in mind. Please make sure you look in the axes, look in the units for that, and make sure that if there is a power there, you're using those numbers. Okay. So, in this video, we have learnt the following. We have examined energy frequency graphs and what we can calculate from them. We've examined current voltage graphs and what we can calculate from them. And we've looked at some possible variations to the graph and how to handle them. For your entrance slip to class, please complete questions 7 to 10 in Chapter 11.5, Check Your Learning PDF, and copy your answers for them into the 4.2.10 space on eLearn. Okay, thanks for listening, guys. Have a great evening.